Okay, let's look into the numerical implementation of von Mises plasticity with no hardening. By the end of part 4, now you will have a clear idea about different types of tensors, von Mises plasticity, what sort of criteria is there when we talk about von Mises plasticity, which is based on the equivalent stress criteria. And we assume that the deviatoric part of the stress tensor is the one which tries to distort or change the shape of the material and is the main cause of plastic deformation in conventional metals. So numerical implementation is very straightforward case of initial yielding. So if I can use the red one. So if I try to explain the numerical implementation of plasticity for an ideally plastic material, let's look at sigma and epsilon plot. When we start deformation in uniaxial case, we always start with the elastic limit, and then once we reach to the yield strength of the material or the strength of the material, we can call it sigma f as well. Then we will have plastic deformation. For ideally plastic material, we will have horizontal line. For strain hardening material, we will have some kind of hardening behavior, which will be the next part of this course. So how this numerical implementation works is for every strain increment, which is the input comes from the finite element solver, for example abacus, if we get an increment of strain delta epsilon and also total strain, then based on this increment we can calculate the current value of the stress. And in uniaxial context, if let's say if our delta epsilon reaches, or based on this strain increment, the stress reaches to this value here, then we can compare this value with the yield strength, and we can see in this diagram as well that this is lower than this value. So we are still in the elastic zone. So our trial value coming for a stress based on the linear elastic solution says that we are still in the elastic zone. So what you will do, you don't need to compute any plastic strains, and you can just update the stress and move to the next increment. However, if our strain increments were such that our trial stress value goes out of or above the yield strength, then in that case we need to use return scheme. So for that increment of strain, you need to come back to the yield surface, and that's called so your trial value was here, so you're predicting the elastic, that's called the elastic predictor step. And if it is higher than this, then you will use the corrector step, and in that case you will bring it down, bring it back to the yield surface of the material, which is this in this case. And this strain will contribute towards the plastic strain in the material, and for uniaxial case this will be equivalent to the equivalent plastic strain increments. And this way it continues, then you go further, and then it keeps on returning back if you are in the plastic zone. And this way you track or you trace this whole curve of the stress strain curve in the real life. So this is how the return mapping scheme really works in the context of yield surface, which is the von Mises yield criterion. If I plot it in terms of principal stress as sigma 1 and sigma 2 in 2D, then as I told you before, it looks something like an ellipse, and these values here are the yield strength of the material, which is sigma y. So this is negative sigma y, this is positive sigma y, this is positive yield strength, and this is negative yield strength. So based on the direction, let's say if you go up to this, we compare that we are inside the yield criterion. Based on the yield criteria I gave you in the last part, we are in the elastic zone, we update the stress, move on. If our prediction shows that we are above this yield surface, this means we need to now use some kind of correction step, and in that case we will use a normality rule based on the flow rule, and we will come normal to the surface back here, and this will give us the increment of equivalent plastic strains, and that will be then stored as an accumulated plastic strain in the material. So this is the overall analogy graphically. So as I said, we will be using return mapping algorithm. I tried to explain to you in 1D and also in 2D cases. Similarly in 3D you will have a cylindrical shape for von Mises criteria, and you will again use the same analogy. So as soon as you are out of the yield surface, you basically have to use radial mapping or return mapping scheme to go back to the yield surface. in all these cases, as we have no hardening, so our yield surface is constant. But in the next part, when we will have isotropic hardening, in that case our yield surface will start to grow, and then we have to really capture that as well, or keep into account that as well while we are doing return mapping algorithm. So first thing is we will compute the trial stress value based on the purely linear elastic response, and that's called the elastic predictor step. So again, in this case I'm using Lamé's constant mu and lambda. If you have Young's modulus E and Poisson's ratio nu, you can use standard elastic relationship to find these values, and vice versa as well. So based on the elastic solution, our stress increment will always be a function of the volumetric part of the elastic strain and the total strain as well, which is more on the shear part, which is trying to change the shape of the material. So this is what you are after. And remember, the elastic strains are generally total strains minus the plastic strain tensor. So total strain comes from the Abacus finite element software. Elastic strains we need to compute to update the stresses, and to compute the elastic strains we need to find out what are the plastic strains if we are in the plastic zone. In order to define the stiffness tensor, so we need to use a fourth order tensor, because the elastic stiffness tensor is a fourth order tensor. So you will have a 6x6 matrix, and for linear isotropic material with two elastic constants, in this case Lamé's constant mu and nu, it's given by this. So again, you can have a look at any linear elastic theory. Okay, so now we know that, and what we do now, we try to compute the trial value of a stress tensor based on the strain increment, as I told you before, coming from the finite element software. We already know this from our linear elastic solution, which I gave in the previous slide. This is the previous stress tensor, which is coming from the previous time increment. So everything is solved incrementally in this case. So once here, everything is Cauchy stress tensor in this case, and we are trying to find out the trial stress value, as I said, which is a predictor value, because we are not sure if it's in the elastic zone or a plastic zone. And then we will update it based on using the previous step value as well. Now we will determine the trial yield function, and for that we need to compute the equivalent stress. So I gave you the relationship for equivalent stress, and this is given by 3/2 deviatoric part of stress tensor times deviatoric part of stress tensor. So it will give you one scalar value, since this is a double inner product in continuum mechanics. So again, if you haven't done any tensor algebra course, so you just have to believe me that when you multiply these two things, it's like a dot product in vector as well, they will become, so double inner products will give you a scalar value here. So you will get one single number as equivalent stress for trial. And in terms of expansion, after you expand it in terms of individual components, you can write it down in this form as well. So if you are really confused with this tensor notation, you can directly use this relationship if you know all the components of your stress tensor to calculate the equivalent stress, which is basically coming from the trial state. Once we have done the equivalent stress, this is a scalar number, we will subtract it from the yield strength, and if it is less than 0, then as I explained before, we are in the, based on this, we are in the elastic zone somewhere. So we don't need to do anything, we just update stresses, and that will be our solution. So we update the trial stress to be the equivalent stress, and also the trial sigma ij to the actual stress tensor, and then we go to the next increment. If this comes out to be greater than 0, right, this means our stress is higher than the equivalent yield strength value. So we need to use this return mapping scheme. In this case, we call it radial return, because we say in the hydrostatic state, 3D stress state, it looks like a circle. Okay, so in this case, we need to use some kind of normality rule, as I told you. So we need to find out the flow direction, and also we need to find out what is the effective plastic strain increment in this step. And for that, we will be using Newton method, because it's a nonlinear equation which we have to solve. In this case, we are dealing with ideal plasticity, as I told you before. That means a horizontal line after the plastic deformation starts. And that's why the tangent moduli of that part of the curve is 0, because the slope of that line is 0. So to determine the incremental plastic strain, we need to solve this equation. And if you again go back and look at the von Mises plasticity theory, where if you are really interested in the whole derivation, then this is kind of the corrector step. So what is happening if our trial stress is higher than the yield strength value, then we need to bring it down to the yield function or to the yield strength value. And this plastic strain contribution basically does that. So if we subtract this contribution, which is the deviatoric part coming from the stress strain relationship, then it will basically does the job of this in return mapping algorithm. So I have tried to simplify it down without confusing you with the overall derivation. You can have a look at many other books and videos where they explain how you come to this relationship here. So the only thing unknown now for us in this case is this increment of equivalent plastic strain, right? So we have to solve for this. And that's what we are doing now. So we need to use Newton method, because in majority of the cases we end up with a non-linear solution where we cannot separate the variables. So to find the solution for delta epsilon p, we need to use an iterative process. So for any iteration I, we need to make this residual to be minimum or 0, right? And for that we use Newton method. If you're not familiar with Newton's method, to get a new value, in this case it's delta epsilon p we are after, but if our unknown is x, so for an updated value of xn plus 1, we will use the previous value of xn, the function at xn, which is this in this case, and then the derivative of the same function with respect to the variable we are after, which is this delta epsilon p. So I'm going to now substitute these values here, and you can see that this one is the updated value, this is from the previous value, equivalent plastic strain increment. This is the residual which is coming from this function here, and then this is the derivative of this whole thing with respect to delta epsilon p, and that's the increment of the equivalent plastic strain. So this way we can find the updated value of equivalent plastic strain. In this case, the stress F is sigma y, because we are dealing with ideal plastic material, and also the slope of the line after the plasticity is 0 because we have no hardening in the material. Later on you will see that this value is not 0, and this also is not constant because it changes, yield strength changes as we start to deform the material. So we will accommodate that, and this needs to be updated as well in numerical implementation, which I will show you later on. So this whole scheme basically concludes when our R becomes 0 for different values of epsilon p. Once the value of the delta epsilon p has been determined, which is the increment of the equivalent plastic strain, we can use a normality condition, which I explained before graphically, and we can determine the stresses based on this formula, which is a function of the deviatoric part of the trial stress, equivalent trial stress, yield strength value, Kronecker delta, and the volumetric part of the trial stress. Okay, and this is just a typical definition based on the trial stress. We are finding the updated values of the stresses. We can also find out the elastic strains and also the plastic strain tensor, which is again given here based on the Newton method, which I explained before. So this way you have updated the stresses and also the elastic and plastic strain tensors. Once we have done that, then the most important part is to find out the consistent material Jacobian, which really then contributes towards the global stiffness matrix of the finite element solver, because this data also goes back to the finite element solver. In order to find the consistent material Jacobian, you need to take a partial derivative of the stress tensor increment with respect to strain tensor increment. And this is the relationship for the stress increment rate. If I substitute everything in the initial stress increment based on all the values and formulas which I have given you in the previous slides, so you can have a go at it and see if you can reach to that. Otherwise, you can look at any textbook and you can find a standard relationship there as well. Also remember, for very large strain version, an additional initial step should be introduced by rotating the stresses, elastic strains, and plastic strain tensors according to Hughes and Wingate algorithm. And for that, we don't need to do anything in Abacus because Abacus already has a subroutine which we can directly call, and this is called ROTSIG. So I'm going to use the same, so I'm not going to go into the details of what to do, what is really happening at the background when you have a large strain version, because in the last strain version, we work with the deformation gradients and not with the strain increments. So